Hello, everyone, and thank you for coming to our presentation entitled Machine Learning Beyond the Cleveland Dataset: Across Cohort Coronary Disease Prediction Using Expanded Clinical Features. Our team consisted of 3 data scientists currently enrolled in the University of San Diego's Masters in Applied Data Science program. Team members include Jun Clemente, Darren Chen, and myself, Graham Ward. Our research centers on the fact that coronary heart disease is the #1 cause of death globally for now over 30 years, according to a World Health Organization report from 2021. For the United States, the American Heart Association reports that it is the leading cause of death within the United States now for over a century. In the past, studies have been focused around only one of these data sets, which is known as the Cleveland dataset. This dataset has 303 observations and a reduced 14 feature dataset. While this is efficient for modeling purposes, our study highlights that this avenue does not accurately act as a representative sample of the global population of heart disease. Thus, the goal of this study is to expand the initial framework by including 3 other locations and beginning with the full 76 feature dataset for each location. This will hopefully increase predictive performance and construct a model that is a more representative sample of the global population of heart disease. The initial merged dataset contained 899 observations spread across 76 predictors and 4 distinct locations, including California, Ohio, Hungary, and Switzerland. By the end of the data cleaning and pre-processing, the dimensions of the dataset were reduced down to 39 predictors. Our target variable, has disease, is a binary target with 0 for no disease and 1 for has disease. It is important to note that the initial raw data has 5 overall severity levels for coronary heart disease. Data was sourced from the University of California, Irvine's machine learning repository.
In our initial data exploration, we assessed the extent and pattern of missingness across all features. On the left, several predictors, most notably CA, thal, and thal time, exhibited high proportions of missing data. To better understand whether this missingness was isolated or systematic, we used an upset plot shown on the right. It revealed that these 3 variables were frequently missing together, suggesting the possibility of non random missingness. To maintain data quality, we applied a missingness threshold. Any feature missing more than 60% of observations were removed from the dataset. The CA predictor was reintroduced later in the process since it was part of the original Cleveland 14 dataset and was deemed clinically relevant. This step helps retain predictive value while minimizing noise and bias introduced by excessive missing data. We examined the distribution of each feature. For example, most of the numerical variables, such as RLDV5, exhibited a strong right skew. To address this, we used median imputation, which is more robust to skewed data than the mean. To preserve potentially valuable information about missingness, we created missingness indicator columns for every variable that had missing values. This allowed our models to learn from not just the imputed values, but also the fact that data was missing in the first place. We also noticed a moderate correlation between years and SIGs, both features related to smoking behavior. Rather than impute them independently, we engineered a new variable called smoke profile, which combined smoking duration and intensity into a single feature. This helped retain interpretability while reducing redundancy in our model input. In the bivariate analysis phase, we examined the relationship between each predictor and the binary disease outcome. For numeric features, we used box plots to compare distributions across disease status. For categorical variables, we used stack proportion plots to assess how category frequencies differed by outcome. We then conducted statistical testing, which is t-tests for numerical variables and chi-square tests for categorical ones, to identify predictors that were significantly associated with the target. To further refine our feature set, we computed Kramer's V for all categorical pairs and removed those that were highly collinear. For instance, we kept LAD-prox due to clinical relevance, but dropped several other artery indicators that were strongly correlated with it. The final data set for modeling included 899 observations and 39 features, including imputed variables and missingness indicators.
Once the data was cleaned and preprocessed, it was split so that we would be training on 70% of the data and validating and testing on the remaining 30. Our study also leverages five-fold cross-validation during the model training process as a resampling strategy in an attempt to reduce the chance of overfitting. 8 unique models were developed to find an optimal classifier and to evaluate their performance with relation to previously developed studies. As a baseline, a logistic regression model was developed along with 3 different penalized variations of the logistic regression: Lasso L1, Ridge L2, and ElasticNet were all developed in conjunction with the logistic regression model. Furthermore, a random forest model was trained on 500 trees and used to account for any nonlinearity and to establish a baseline ensemble tree model. The seventh model developed was a partial least squares discriminant analysis model, specializing in reducing the number of features to components which capture the maximum covariance amongst the features. It was found that the optimal number of components to be 5. And then finally, our team developed a k-nearest neighbors model, which is a powerful predictive tool to classify new samples based on their closest data neighbors. The optimal value of k, which led to the highest AUC, was found to be 21 neighbors.
We applied stratified five-fold cross-validation to tune all models. Each model underwent grid search for optimal hyperparameters using caret. ROC AUC was the main evaluation metric to prioritize discriminative ability between the classes, complemented by sensitivity, specificity, and accuracy. When evaluating model performance using ROC AUC as the primary metric, partially squares discriminant analysis (PLSDA) emerged as the top performer with an AUC of 0.911, indicating excellent discriminative ability in identifying heart disease, while random forest achieved the highest specificity at 0.85 and shared the highest accuracy at 0.821. Its interpretability is limited due to its ensemble nature. On the other hand, KNN, which also tied for highest accuracy and demonstrated the highest sensitivity at 0.848, offers greater transparency in decision making and is more interpretable than random forest. In evaluating heart disease models, PLSDA and KNN emerged as top contenders. PLSDA offered the highest ROC AUC of 0.91 with balanced sensitivity and specificity, making it ideal for clinical deployment due to its strong performance and interpretability through component loadings. KNN, with the highest sensitivity of 0.85 and tied for top accuracy 0.82, provides case-based transparency, making it well suited for clinical explanations. While random forest is also performed well, its black box nature limits interpretability. So we selected PLSDA as the primary model for its balanced performance and diagnostic value, and KNN as a supplementary tool for explainability and cross-validation. When using these models to other data sets, we recommend the following limitations to consider. The data were collected only from 4 geographical sites, which may limit generalizability. Class imbalance in the outcome variable could bias predictions towards majority classes. Additionally, missing values were imputed using simple methods, which may introduce bias. Future research should aim to improve or incorporate more diverse populations and adopt robust imputation techniques such as mice, and extend the modeling approach to the original 5-level outcome classification for improved clinical relevance. Thank you for taking the time to watch our presentation and for your guidance throughout this course.